See, what we shall show here is the cause of rotational motion. Cause of rotational motion is the centripetal force. Let's see how we get it. See, this r vector can be represented as I cap x plus j cap y. Now, if you plug in the values of x and y, that's I cap r cos theta plus j cap r sin theta. Now, what is momentum? Momentum P, that is mass times velocity. Now, this particle is moving and the velocity is tangential naturally. So, let us find the velocity first. Now, this is r. So, what is v? V is dr dt, right? So, if you differentiate this, see, this r is constant. This r is not constant, r vector is not constant, but this magnitude of r is constant for a uniform circular motion, and I cap, j cap are also constant. Why? Because they are unit vectors along x and along y. So, if I differentiate, this constant will come from then ddt of cos theta. So, ddt of cosine theta plus j cap r ddt of sin theta. Now, watch this. What is ddt of cos theta? So, that is minus sin theta into d theta dt, right? So, that is I cap r minus sin theta times d theta dt. That's the chain rule of differentiation, everybody knows. Then it's j cap r, this is cos theta times d theta dt, right? Now, what is d theta dt? D theta dt is basically change of the angle. So, that's the uniform circular motion, that's the angular velocity, right? Now, if you plug in it here, then I cap r sin theta times omega plus j cap r cosine theta times omega. So, this is V, but what we need? We need momentum. Momentum is already there. What? So, let's write P. What is P? P is mass times V. If you multiply with mass, so if you multiply this whole thing with mass, you get the momentum. But the momentum is not enough. What is important is we need the force. So, what is force? F is rate of change of momentum, right? So, you need to differentiate this. Now, if you differentiate this, what are the constants? So, ddt means mass will be multiplied with this, mass will be multiplied with this, and this mass is constant. So, take it out, m times I cap r. So, this is a minus sign. Oh, okay. Omega is also constant because it's a uniform circular motion. So, it's moving with a constant speed. So, omega is constant. Now, again, this ddt will be applied on sin theta. So, ddt of sin theta means, again, by chain rule of differentiation, it is cos theta times d theta dt. So, that is another omega, okay, plus on the second term, this mass will be here, then j cap, then r, then this omega will be here. Now, ddt of cos theta is, so that's minus sin theta times d theta dt, that's omega. Now, if you write it clearly and take this m omega times omega means omega square out. So, this is m omega square, and if you keep the rest of the term inside this parenthesis, you get minus I cap, or in this bracket, minus I cap r cosine theta minus j cap r sine theta, right? Now you can easily do one thing, you can take this minus common and take it out. Okay. Now what is this? See, this is r itself, so r is coming back. So minus m omega square r vector. This is what? This is the force. If you inspect this force, you can easily see that this is directed radially inward. Now let's write it explicitly. Minus m omega square r times r cap. R cap is the unit vector. So r cap is the unit vector outside, right? But you have a negative sign here. So this is the magnitude of the force, m omega square r. So what is this force? This is the centripetal force. This is the centripetal force. This centripetal force is the cause of circular motion. This is always attractive, and the examples are the gravitational force. If a stellar object is moving in a circular path, the gravitational force is the centripetal force. You can see this, where is the pendulum? That ball. See, this, if this rotates in a horizontal circle, the tension, that means the component of tension along the horizon is the centripetal force. That means if you figure it out like this, suppose this is rotating in a horizontal circle, okay, if this is L, now this is the tension T, and suppose this is theta. If this is theta, this is also theta. Let me, this is T, right? So the component of T along the center of this circle, or radial inward, is the centripetal force, which is m omega square r. So there are many cases where you can find that these centripetal forces will be acting radially inward, and this is an explicit proof that the centripetal force is m omega square r and is radially inward. I have explicitly used vectors. My habit is I have a habit of actually using vectors a lot. I use vectors a lot, and many problems become very simple if you use vectors. Let's do this, practice this, and I have few cases. For example, this is one case, another is the gravitational force, the death well. There is also a cause of motion is the friction, the component of friction which acts radially inward. And suppose the disk, disk means the person who dance on a rotating disk, there also friction acts as a centripetal force. There are a lot of cases where this friction acts as a centripetal force. Most of the cases where the car turns, okay. And there are a few other cases where banking is done to generate a centripetal force. Most importantly, you have to generate this, because you need to change this momentum, right? You need to change this momentum, because this is the velocity. When it comes here, the velocity changes, the direction changes. So as the direction changes, so the momentum changes. So you need to apply an force to change the momentum, and that should be the centripetal force as far as rotational uniform circular motion is concerned. Thank you.